Hey everyone, and welcome. Today, we're going to deconstruct something you've probably seen a million times, but maybe never really thought about: the denture. We know what they do, of course, but the sheer amount of material science packed into one of these is, well, it's just incredible. I mean, just look at this. It seems pretty simple, right? Some pink plastic, some fake teeth. But have you ever stopped to wonder what that pink base is actually made of and why that one material has to pass an insane number of tests to even be considered for the job? The demands placed on it are just, wow. All right, so to really get this, we have to start at the beginning. Let's define what we're even talking about when we say the denture base. So here's the official definition. The denture base is basically the pink part. It's the foundation that rests on your gums, supports the whole structure, and of course holds those artificial teeth right where they need to be. Think of it like the chassis of a car. Everything is built on it. You know, we haven't always used the amazing materials we have today. Before about 1940, the go-to was something called vulcanite, which was basically a type of hardened rubber. But it had some huge problems. It was tough to make it look like real gums, and even worse, it could get pretty gross and unhygienic over time. So that sent scientists on a search for something way better, which led us to today's champion, acrylic resin. So how do you actually turn raw ingredients into a perfectly fitted denture? Well, the process is this really cool mix of chemistry and artistry. It all starts with these two things: a specially pigmented powder, which is a polymer, and a liquid, which is the monomer. A dental technician mixes them together and they start to react, forming this workable, almost dough-like material. And this is how they use that dough. It's called the dough molding method, and it's the most common way it's done. First, they make a super precise mold from a wax model of the patient's mouth. Then, they melt out all the wax and pack that acrylic dough right into the empty space. The whole thing gets cured with heat, which hardens the acrylic and actually chemically bonds it to the teeth. It's a really meticulous process, but it's how you get that perfect custom fit. Okay, now for the really fascinating part. For any material to even be considered for this job, it has to survive an absolute gauntlet of tests. We're talking physical, mechanical, and biological. Let's kick things off with the physical properties. So first, we gotta understand this key concept called the glass transition temperature, or TG. The best way to think about it is like a chocolate bar on a hot day, right? At room temp, it's hard, it's brittle. But as it heats up, it doesn't just melt instantly into a puddle. It first goes through this soft, kind of rubbery phase. For a polymer, that exact point of change is its TG. So, why on earth does this matter? Well, think about it. You drink a hot cup of coffee or tea, and the temperature in your mouth can shoot up to 70 degrees Celsius. The denture base absolutely needs a high TG so it stays rock solid and doesn't get soft or warp out of shape. It's got to keep that perfect fit. But that's not all. It also needs amazing dimensional stability, so it doesn't slowly change shape over the years. It has to have a low specific gravity, which is a fancy way of saying it needs to be lightweight. That's super important for an upper denture that's fighting gravity all day long. It also needs high thermal conductivity, so you can actually feel hot and cold and don't burn yourself. And finally, this one is a huge safety feature. It has to be radio-opaque, meaning it shows up on an X-ray in case it's ever accidentally swallowed. All right, time for a quick knowledge check. Based on what we just talked about, a denture's high glass transition temperature is crucial for what reason? Yep, it's B. It's all about making sure it can resist warping from that hot cup of coffee. Okay, physical tests are done. Next up is the mechanical grind. A denture has to put up with incredible forces from chewing, day after day, year after year, not to mention the occasional accident. So this table breaks down the different kinds of strength a denture needs, and they're not all the same thing. First, it needs a high modulus of elasticity. That just means it's stiff and doesn't bend easily. It needs high flexural strength to resist snapping when it does flex. Then there's fatigue life, which is absolutely critical. That's its ability to handle thousands of tiny, repeated stresses from chewing. And finally, impact strength, so it doesn't shatter if you accidentally drop it in the sink. And that point about fatigue is so important. This quote nulls it. The most common way a denture breaks, while it's actually in your mouth, isn't from one big chomp. It's from fatigue, all those tiny stresses adding up over time, creating a crack. This diagram shows that process perfectly. Every time you bite down, an upper denture flexes just a little bit, right in the middle. Do that thousands and thousands of times, and a tiny microscopic crack can start to form and grow, until one day you get that classic crack right down the midline. It's a perfect example of fatigue failure in action. Okay, another quick question for you. Which property helps a denture survive that accidental drop onto the bathroom floor? That would be C, impact strength, its ability to take a sudden hit. We are in the home stretch now. The material has passed the physical and mechanical tests, but there are still a few final but absolutely crucial hurdles to clear. And here they are on the final checklist. Chemically, it's got to be totally inert. It can't dissolve in saliva or absorb water. Biologically, and this is a big one, it must be non-toxic and non-irritating. It also can't be a material that bacteria and fungi love to grow on. And finally, you've got the practical stuff. It has to be affordable, easy for the lab techs to use, and super important, easy to repair if something does happen. All right, last question. Biologically speaking, what's the most important thing a denture-based material has to be? Easy, it's D. It absolutely has to be non-toxic and non-irritant. Patient safety is always number one. So, here's the big takeaway from all of this. Acrylic resin isn't actually perfect at any single one of these things. You can find materials that are stronger or lighter or have a higher TG. But no other material we've found does such an amazing job of balancing all of these competing, intense demands. It's the ultimate all-rounder, the perfect compromise, and that's why it's been the gold standard for over 80 years. And that really leaves us with a fascinating question for the future, right? Acrylic has ruled this world for decades. But with all the advances we're seeing in 3D printing and incredible new polymers, what will the perfect denture of tomorrow be made of? That's what scientists are trying to figure out right now. Have you ever stopped to wonder what dentures are actually made of? It's way more than just, a piece of plastic. Today, we're going to deconstruct the surprisingly complex chemistry that turns a simple powder and liquid into an advanced medical device. Let's jump right in. So it all starts with these two parts, a specialized powder and a potent liquid. When you mix them together, something pretty incredible happens. They transform from this basic stuff into a precise, durable, and really lifelike dental prosthetic. So the big question is, what's actually inside this box that allows that remarkable transformation to happen? Here's our game plan. We'll start by mapping out a denture's secret ingredients. Then we'll explore the powder, and then the liquid. After that, we'll look at the chemistry of how it all hardens, and finally, we'll wrap up with a quick quiz to see what you've learned. Okay, first up, let's get a bird's eye view of all the players involved in creating this stuff. You can think of it like a chemical recipe, where every single ingredient has a really critical job to do. Here's our whole ingredient list, broken down into two teams, Team Powder and Team Liquid. In the powders corner, you've got the main structural polymer, an initiator to get the reaction started, and pigments for the color. Then, on the liquid side, we've got the monomer. That's kind of like the reactive glue, a cross-linking agent for strength, an inhibitor for protection, and sometimes an activator. Let's meet each of them one by one. All right, let's zoom in on the powder first. Now, this isn't just any old dust. It's a very carefully engineered material that literally forms the backbone of the final denture. So what are these tiny particles actually made of? The star of the powder is polymethyl methacrylate. I know, it's a mouthful, so we'll just call it PMMA. The best way to think of these are like tiny pre-made Lego bricks. They make up the bulk of the denture and give it its fundamental strength and shape. And check this out. This is what those PMMA beads look like up close, under a powerful microscope. You're looking at thousands of these little tiny spheres. What's really cool is that each one of these beads is already a polymer, a long chain of molecules just waiting to be cemented together into one solid mass. Next up in the powder is the initiator, which is usually benzoyl peroxide. Its whole job is to be the starting pistol for the hardening reaction. It just kind of hangs out in there, totally dormant, mixed in with all those PMMA beads, until it gets the right signal to kick everything off. And finally, for the powder, we have the pigments. I mean, without these, the PMMA would just be a clear, glass-like plastic. Pigments are added to give the denture that natural pink, gum-like color. And get this, sometimes tiny red fibers are even added to mimic the look of small blood vessels. It's all about making it look real. Okay, so that's Team Powder. Now let's switch over to the other bottle and see what the liquid is all about. This isn't just a simple solvent. It's a whole cocktail of reactive chemicals designed to bring that powder to life. The star of the liquid team is the monomer, methyl methacrylate, or MMA. Now, you probably noticed that name is super similar to the powder's name, PMMA. That's no accident. This liquid MMA is the single molecule, that's the mono part, that will link together to become the solid polymer, the poly part. It basically acts as the glue that binds all those pre-made PMMA beads into one solid structure. To make the final material even tougher, a cross-linking agent is added. Think of it like this. If the polymer chains are like two long ladders lying side by side, the cross-linking agent adds rungs between the ladders, locking them together. This makes the whole thing way more resistant to fracturing and wear. So you might be wondering, if this liquid is so reactive, why doesn't it just harden right there in the bottle? Well, that is an excellent question, and the answer is the inhibitor, usually hydroquinone. It acts like a bodyguard, protecting the liquid and giving it a long shelf life by stopping any unwanted reactions from starting. How it does this is actually pretty elegant. This diagram gives us a great look at how it works on a molecular level. If a stray active radical, let's call it X, shows up, our inhibitor bodyguard, Y, immediately jumps in and intercepts it. They react with each other and form a new molecule, Z, that is completely harmless and can't start the hardening process. So why is this new Z molecule so stable? Well, as this diagram shows, that reactive energy, that unpaired electron, isn't stuck in one place. It gets shared and spread out all across the molecule's ring structure. This spreading out of energy makes the new radical incredibly stable and effectively neutralizes the fret. It's a very clever bit of chemistry. Lastly, some versions of the liquid, the self-curing types, also contain an activator. This is the final piece of our puzzle. When the liquid and powder are mixed, the activator's job is to find the initiator that's in the powder and give it the chemical go signal to start the reaction right away, no heat needed. So we've met all the ingredients on Team Powder and Team Liquid. Now for the main event. What happens at the moment you finally mix them together? It's a rapid and really elegant chain reaction. The instant they're mixed, the activator in the liquid finds the initiator in the powder. This creates a huge burst of highly reactive things called free radicals. These radicals immediately attack the liquid monomer, causing it to polymerize or form solid chains, which then weaves through and binds all those powder beads into one dense, hard, solid structure. Okay, we've covered a ton of ground, from the basic ingredients all the way to the pretty clever chemistry of how it all works. So let's do a quick knowledge check to see what stuck with you. First question for you, think about what needs to happen, or actually what needs to not happen, inside that bottle of liquid while it's just sitting on the shelf. What's the inhibitor's main job? That's right, the answer is C, to prolong shelf life. The inhibitor is that bodyguard we talked about. Its entire purpose is to prevent the reactive monomer from hardening prematurely, making sure the product is stable until it's ready to be used. All right, second question. Remember that magnified image we saw of all those tiny spheres? What are those microscopic building blocks that form the foundation of the denture made of? The correct answer is B, polymethyl methacrylate. And this really highlights that key distinction we talked about. The polymethyl methacrylate, or PMMA, is the solid polymer powder. The methyl methacrylate, or MMA, is the liquid monomer that acts as the glue. And for our final thought, the balance of these chemicals is just so precise. How do you think changing the amount of just one ingredient, like that cross-linking agent, might affect the final properties of a denture for a patient? Well, based on what we've learned, less of it might make the material more brittle, while too much could make it too rigid. It's a fantastic example of how this precise chemistry directly impacts the quality of medical devices we rely on every single day. You know, making a denture isn't just art. It's more like a high-stakes scientific recipe. Every single ingredient, every measurement, every step, it's all absolutely critical. If you get one little thing wrong, the whole structure could fail. So let's pull back the curtain and break down the science behind building that perfect acrylic smile, step by step. So here's our roadmap. We're going to break this down into 6 key parts. We'll start with the basics, the ingredients, then get into nailing that perfect mix. After that, we'll see how pressure becomes our best friend, explore the wild science of curing, touch on some cool modern alternatives, and then, of course, we'll test what you've learned. Okay, so let's start at the very beginning with our 2 core components. We've got a polymer, which is a powder, and a monomer, which is a liquid. The easiest way to think about it is this. The monomer liquid is the glue that's going to link all that polymer powder together to make one solid piece.
The entire process, literally everything, hinges on getting this combination just right.
So why are we so obsessed with the mix? Well, because this is where we tackle the single biggest challenge with this material right from the very start. And that challenge is shrinkage.
That's right, 21%. If we were to try and make a denture from just the pure monomer liquid, the final product would shrink by a staggering 21%. I mean, that's like a 5-foot person shrinking to just under 4 feet. Trying to make something fit a person's mouth precisely is just impossible with that much change. This is the problem we have to solve.
And the solution is pretty brilliant, actually. We mix that liquid monomer with the pre-made polymer powder. See, that powder's already solid, it's stable, it's not going to shrink anymore. By mixing it in, we're basically pre-shrinking the vast majority of our material. Now, only the liquid monomer part has to polymerize and shrink. And by using that super precise 2.5-to-1 ratio by weight, we slash that massive shrinkage all the way down to a much more manageable 5 to 6%. As you mix them, the material goes through these 4 really distinct stages. First, it feels sandy. Then it quickly becomes sticky, and it'll form these little strings if you touch it. Next up is the magic moment, the dough stage. It's just like modeling clay. This is the perfect time for packing. But you have to be quick, because if you wait too long, it becomes tough and rubbery, and you've completely missed your window. And this right here, this is our first potential point of failure. If your ratio is off, say too much powder, or you forget to cover the mixing jar and some of that monomer liquid evaporates, you get this, granular porosity. What's happening is there just isn't enough of that liquid glue to fully coat and bind all the powder beads together, leaving these tiny gaps. The result? A weak, porous structure that looks all blotchy and kind of opaque. All right, so once we've got our perfect dough, it's time to get it into the mold. And this brings us to the hero of our next step, immense pressure. Now, this isn't just about shaping the dough. It's about actively fighting against the material's built-in flaws. So here's what the setup looks like. The acrylic dough gets packed into this 2-part gypsum mold. We use gypsum because it's super stable and can capture all the fine details. This whole thing is then held in a heavy metal flask, which has to be strong enough to handle the incredible pressures we're about to apply. That empty space you see, that is the exact negative shape of the final denture. The key thing to remember here is that applying all that pressure with a bench press does 3 absolutely vital things. First, it forces that dough into every single tiny crevice of the mold, which gives us a perfect fit. Second, it helps compensate for that 5 to 6% shrinkage we've been talking about. And third, it makes sure the final denture isn't too thick, which would cause a problem we call a raised bite. And this brings us right to our second major defect. If you don't use enough dough to begin with, or you just don't apply enough pressure during the packing stage, you end up with contraction porosity. As the material shrinks while it's curing, these little voids, basically empty spaces, will form all throughout the denture base, making it super weak and totally unreliable. So we've mixed it perfectly, we've packed it under intense pressure, and now it's time for the scientific climax, curing. This is the process where we use heat to kick off a chemical reaction that transforms our soft, pliable dough into a hard, durable, and finished product. Take a look at this graph. Up the side, you've got temperature, and along the bottom is time in hours. It's tracking the temperature deep inside the acrylic itself. Now, curve A shows the perfect way to do it, heating slowly at 70 degrees Celsius for hours. See how the temperature rises but stays nice and controlled? Curve B, well, that's the disaster scenario. That's what happens when you just chuck the flask directly into boiling water. Look at that massive, insane temperature spike to over 150 degrees Celsius. So why is that huge spike so bad? Well, the boiling point of our liquid monomer is 100.3 degrees Celsius. But here's the tricky part. The chemical reaction itself is highly exothermic. That means it generates its own heat, like a tiny engine running inside the dough. So if the outside heat plus the reaction's own heat pushes the internal temperature above that boiling point, the monomer will literally start to boil. And this picture shows you exactly what happens. That boiling monomer creates bubbles, leading to our third major defect, gaseous porosity. These voids usually pop up in the thickest parts of the denture, where it's hardest for all that heat to escape. And as you can imagine, this severely compromises the strength of the final product. Okay, so we know the slow heat curing process is fantastic for making a strong, brand new denture, but what if you just need a quick repair? Well, that's where some of these modern alternatives come into play, and they use different tricks to kickstart that curing process. This table really lays out the trade-offs perfectly. Heat curing, our hero so far, gives you a long working time and the strongest result, perfect for new dentures. Cold cure is super fast, which is great for a quick chairside repair, but you do give up some strength and working time. And then there's light-activated resins, which give you the ultimate control. Nothing happens until you shine that special light, which is why they're used for really specialized, high-precision jobs. All right, you have absorbed a ton of information. So now it's time to put that new knowledge to the test with a few quick questions, covering the biggest concepts we've talked about. Ready? First question. To knock down that massive initial shrinkage, what's the ideal powder-to-liquid ratio by weight? If you said C, 2.5 to 1, you are absolutely correct. That's the sweet spot that takes shrinkage from that crazy 21% all the way down to about 6%, while still keeping the dough workable. Question 2, remember those nasty internal bubbles we called gaseous porosity? Take a look at the options. What's the most likely way to cause that? The answer is C. That's right. Placing the flask directly into boiling water causes that rapid, uncontrolled temperature spike, which makes the monomer boil and creates all those internal voids. And for our final question, if you don't apply enough muscle, enough pressure during that packing stage, which one of these defects is the direct result? And the correct answer is C, contraction porosity. Without that crucial pressure, the material's own natural shrinkage creates voids that weaken the entire structure. And really, that drives home the main point of all this. From that initial powder-to-liquid ratio all the way to the final slow cure, every single step is a deliberate battle against the material's natural flaws. It's just a perfect example of how science and precision come together to create something that's both functional and beautiful.
You know, when you look at the pink acrylic on a denture, it seems pretty simple, right? Just a solid piece of plastic. But what if I told you that if we could zoom way in, down to the microscopic level, we'd find this incredibly complex, engineered world? Well, that's exactly what we're going to do. Let's dive in. So here's the game plan for this explainer. We'll start by showing you how acrylic is basically a composite in disguise. Then we'll meet the two main players, the beads and the matrix. We'll see how they form their bond, what makes that connection strong, and then we'll get into some really cool differences between the two. And of course, we'll wrap it all up with a quick quiz to see what you've learned. All right, first up, a composite in disguise. Yeah, it looks like one single uniform thing, but that piece of acrylic is actually a super clever mix of different materials all working together. To really get this, we first need to understand what a composite material even is. The best way to think about it, a chocolate chip cookie. Seriously, you've got the dough and you've got the chocolate chips. You mix them together to make one awesome thing, the cookie. But the dough and the chips are still separate parts you can see. That's a composite. And just like our cookie, set acrylic is a composite system. It's made of these tiny pre-made plastic beads. Those are our chocolate chips that are all glued together by a new material that forms around them, which we call the matrix. That's our dough. These are the two key players we need to understand. So let's properly introduce our two components, the stars of the show, the beads and the matrix. Okay, so everything starts with two things, a powder and a liquid. The powder is made of these teeny tiny beads of a polymer. It's called polymethyl methacrylate, which is a mouthful, I know. Just think of them as the bricks. Then you have the liquid, which is a monomer. That's basically the unset mortar that's going to harden and bind all the bricks together. Simple, right? Bricks and mortar. So how in the world do we get from a separate powder and liquid to one incredibly tough, solid material? Let's break down how that amazing bond actually forms. This is where the magic happens. It all happens in three main stages. First, when you mix them, the liquid monomer completely floods the area and surrounds all the polymer beads. Then, and this part is absolutely crucial, the liquid doesn't just sit on the surface. It actually starts to penetrate, soaking into the outer layers of the beads, making them soft and kind of sticky. And finally, the liquid itself has a chemical reaction called polymerization. It hardens into a solid, locking those softened beads and the new matrix together into one solid piece. And boom, this is what it actually looks like. This is a real micrograph. You can clearly see those round beads, our little islands, just locked in place by that surrounding matrix. Our C. See? The beads didn't melt or disappear. They've been fused into this brand new unified structure. It's pretty amazing. Now, the fancy scientific term for this cool structure is interpenetrating networks of polymers. It sounds super complex, right? But all it really means is that the matrix has literally woven itself into the beads, creating this tangled, interwoven lock between the two parts.
This is the secret sauce that gives the final material all its strength.
But here's the thing. The strength of that bond isn't guaranteed. There are a few key things that can really affect how well these networks form, and ultimately, how strong the final material ends up being.
So, 3 factors are really important here. First, the molecular weight of the polymer in the beads. You can just think of this as how big and complex the plastic chains are. That affects how they soften. Second, the polymer to monomer ratio. This is critical. It's basically just how much powder you mix with how much liquid. And finally, contact time. The longer the liquid is in contact with the beads before it hardens, the more time it has to soak in and do its job. Getting that mix right is so important. This quote really nails it. If you have a dry mix with not enough liquid, you're going to get a weak structure. It makes sense, right? You just don't have enough mortar to properly soak into and grab onto all the bricks, and you end up with weak links all over the place.
Okay, now we're going to get a little more advanced and take a deeper look at something really fascinating. We know the beads in the matrix are different, but there's a really interesting paradox in how they behave.
So check out this table. The original beads are uncross-linked. Imagine their polymer chains are like individual strands of spaghetti in a bowl. Because they're separate, they can completely dissolve in certain solvents. But the new matrix that forms around them is cross-linked. Now, imagine all those spaghetti strands are chemically tied together, forming a net. You can't dissolve that net, can you? It can only absorb liquid and swell up. That robust, net-like structure is what makes the final material so incredibly durable.
All right, you've soaked up a ton of info. So how about a quick pop quiz to see how well these ideas have stuck? Okay, question number 1. What is the primary role of the liquid monomer in set acrylic material? Is it A, to act as a filler, B, to dissolve the beads completely, C, to penetrate and bind the polymer beads, or D, to add color to the material? Take a second.
And the correct answer is C. Its most important job, by far, is to soak into those beads and then harden, binding the whole thing together. It's the active ingredient, our mortar.
All right, question 2. This one's a little trickier. A key difference between the bead and matrix phase is that the matrix is typically A, weaker and more soluble, B, lighter in color, C, cross-linked and insoluble, or D, made of a different base chemical.
Yep, the answer is C again. Cross-linked and insoluble. That chemical netting we talked about is what gives the matrix its unique properties, and it's absolutely fundamental to the final strength of the whole composite.
And that brings us to the end of our microscopic journey for today. The remaining sections will be discussed in upcoming parts.
You know, have you ever really looked at a denture and just wondered, what is that thing actually made of? I mean, it looks pretty simple, right? But behind that smile, there's some seriously fascinating science going on. So let's dive into the world of denture acrylics, because understanding what they are and why they're made that way, well, it reveals this whole hidden world of clever engineering and really important trade-offs. So here's our game plan. First, we're going to meet our main character, acrylic resin. Then we'll get into its physical and mechanical properties. You know, how it looks, feels, and holds up under pressure. After that, we'll connect all that science to the real world of denture care and some common problems. And to wrap it all up, we'll have a quick quiz to see what stuck. Sound good? Let's go. All right, first things first, let's meet acrylic resin. Now, before a material can even dream of being used in a denture, it has to follow a really strict set of rules. Think of it like a piece of sports equipment. It has to be officially certified to make sure it's safe and it actually works. And this, right here, this is the official rule book. It's called ISO 1567. This standard basically sets the minimum passing grade for everything: its strength, how much water it soaks up, and something really important called residual monomer. Just think of that as leftover, unreacted ingredients. You want that number to be as low as humanly possible for safety. This is the checklist that protects patients. Okay, let's move on to the physical properties. Now, these are the characteristics you can actually see and feel. They're what directly impacts how comfortable and just how livable a denture is for the person wearing it every single day. So the first, and honestly probably the most important physical property we need to talk about, is something called the glass transition temperature. The easiest way to wrap your head around this, picture a chocolate bar you left in a hot car. You know how it goes from being hard and snappy to soft and gooey? That temperature where it makes the switch, that's its glass transition temperature, or TG for short. For the most common kind of denture acrylic out there, that chocolate melting point is right around 105 degrees Celsius. Now, I know what you're thinking, that sounds crazy high. But it has some huge real-world consequences, especially when it comes to something as simple as cleaning. Which leads us to the million-dollar question, right? If this stuff starts getting soft at 105 degrees, then how hot is too hot when you're just trying to clean it in your sink at home? And here is the critical piece of advice. You have to stay way, way below that glass transition temperature. The official rule is to avoid any water hotter than 65 degrees Celsius. See, if you get too close to that TG, you can accidentally release all the tiny stresses locked inside the plastic, causing it to warp. And once it's warped, that's it. It's permanent. The denture will never fit right again.
But there is more to the story, of course. On the plus side, the appearance is fantastic. You can match it to pretty much any gum color. It's also super lightweight, which is a huge deal for helping an upper denture stay put. But then there are the downsides. It's a really poor conductor of heat, which means you might not feel how hot your coffee is right away. And the biggest disadvantage, honestly, is that it's radiolucent. That's a fancy word meaning it's invisible on an X-ray. And that is a serious, serious problem if a piece ever breaks off and is accidentally swallowed or inhaled.
Okay, time for the stress test. Let's really put this material through its paces. Mechanical properties are all about how acrylic resin handles force. How strong is it really? How stiff is it? And, how does it compare to the heavy hitters in dentistry like the metal alloys?
Well, this table tells a pretty dramatic story. We're looking at three main things here. Modulus of elasticity, that's just a scientific way of saying stiffness. How much does it bend? Tensile strength is how hard you can pull on it before it snaps. And hardness is pretty straightforward. How well does it resist getting scratched? And as you can see, compared to a metal like cobalt chrome, acrylic resin isn't even playing in the same league. I mean, let's just visualize that stiffness difference for a second. Look at this. Acrylic resin clocks in at about 2.5 gigapascals, and the metal alloy, 220. It's an absolutely massive difference. This is why we say acrylic is a flexible material. It's got some give. The metal, on the other hand, is incredibly rigid. And it's the exact same story when we look at strength. The acrylic comes in at around 85 megapascals. The cobalt chrome alloy is literally 10 times stronger, at 850. So the takeaway here is really simple. Acrylic is, relatively speaking, a pretty weak material, and that goes a long way to explaining why, sometimes, dentures break. So how do they break in the real world? It usually comes down to one of two things. First, there's fatigue. Think about it. Thousands and thousands of chewing cycles every day. That constant tiny flexing can eventually start a crack that just keeps spreading. The other way is impact. Acrylic is brittle. Drop it on a hard tile floor, and that sudden shock can be enough to fracture it instantly. All right, so we've covered the lab science. Now let's connect all of that back to daily life. How do these properties we've been talking about show up as common problems and influence the care instructions that patients get? One really common issue is something called crazing. If you look closely at an older denture, you might see these tiny, microscopic cracks all over the surface. They might look harmless, but over time, each one of those little cracks acts as a weak point, which can compromise the strength of the whole denture. So what causes this crazing? Well, there are three main culprits. The one that affects patients the most is just constant wetting and then drying out. That cycle puts stress on the material's surface, and that is exactly why people are always told to keep their dentures in water when they're not wearing them. The other two causes are a bit more technical, having to do with how porcelain teeth expand differently than the base or from chemicals used during a repair. And look, this is not a small problem. If you want some perspective on just how limited this material can be, get a load of this statistic. Back in 1997, it was estimated that over 1 million denture repairs were needed in the UK in a single year. That's a staggering number, and it really drives home how much the material's weakness costs in both money and hassle. Okay, we have covered a ton of ground, from why you shouldn't use hot water, all the way to why dentures can break. So let's do a quick little quiz to help lock in some of these key ideas. Ready? First question for you. Why is it a terrible idea to clean your dentures with boiling or even just very hot water? Have a look at your options. And the correct answer is D. Absolutely. If the water gets too hot, you start creeping up on that glass transition temperature. The acrylic softens, distorts, and that's it. The fit is ruined for good. All right, last question. When you stack acrylic resin up against those tough dental metal alloys, what's the verdict? Think back to those bar charts. How would you best describe it? And the answer is C, weaker and more flexible.
That's the key takeaway. When you compare it to metal, acrylic is considered a soft, weak, and flexible material. And while that actually makes it easier to work with, it also explains its limits when it comes to long-term strength. So, at the end of the day, acrylic resin is a material all about careful trade-offs. It's a balance, right? You get amazing aesthetics and it's affordable, but you trade off some mechanical strength. Understanding this science is absolutely crucial for anyone who designs, uses, or takes care of a denture. The remaining sections will be discussed in upcoming parts. Dentures. Specifically, we're going to talk about the stuff they're made of, acrylic resin. Now, you might just see a piece of plastic, but trust me, it's a little marvel of material science, balancing all these different properties in some really surprising ways. So, to kick things off, let me ask you this. How do you think the material in a denture stacks up against something we all know is super strong, like solid stainless steel? It sounds like a crazy comparison, right? But it's actually the perfect way to frame the incredible job this material has to do. And to get to the bottom of that question, we've got to start with the basics. We need to look at the fundamental mechanical properties of acrylic resin. It's really a tale of two materials, a constant search for that perfect sweet spot between being strong and being flexible. Okay, before we even look at any numbers, there's one key idea we need to get our heads around, the modulus of elasticity. It sounds complicated, but all it really means is stiffness. Just think of it like this. A high number means something is super rigid, it doesn't want to bend, that's steel. A low number means it's got more give, it's more flexible, and that's our acrylic. This one concept is absolutely crucial for how a denture works. All right, now let's look at the data, because this is where the story really comes to life. Check out that modulus of elasticity. You've got acrylic resin down here at 2.5 gigapascals, and stainless steel is way up there at a whopping 220. I mean, that just shows you how much more flexible acrylic is. And it's the same thing with tensile strength. That's how hard you can pull on it before it snaps. Acrylic is at 85 megapascals, steel is at 1,000. But the real kicker is in that last column. Hardness. Acrylic resin gets a score of just 20 on the Vickers hardness scale. You want to guess what stainless steel gets? 400. That means the acrylic is literally 20 times softer, and this shows you the trade-off perfectly. It's what makes a denture comfortable enough to wear, but it's also why it can get scratched or wear down over time. It's just designed for a totally different job than steel. So we've got a good handle on the physical side of things, but believe it or not, that's only half the story. Now we're going to zoom in and take a look at the invisible world inside the material itself, the chemical and biological stuff that's happening all the time. You might be surprised to find out that this material is anything but static. You see, a denture isn't just some inert object. It's living inside a dynamic, wet, and very active environment, the human mouth. And from the very first moment it's put in, it starts to change and react in all these subtle little ways. For example, acrylic resin acts kind of like a very, very slow sponge. It can actually absorb water, up to about 2% of its own weight. Now, this constant cycle of water getting in and out can cause tiny little surface cracks called crazing. It also means that the surface can become a home for tiny organisms like Candida albicans if it isn't cleaned right. This is why daily soaking and cleaning is so important. It's not just about feeling fresh, it's about protecting the material itself. This brings us to something that people who wear dentures sometimes notice. A denture can start to get these white patches, and a lot of times, people think their cleaning solution is somehow bleaching it. But is that what's really going on? Nope, not at all. Have a look at this cross-section. That whitening you see isn't a color change, it's a physical, structural change deep inside the resin. Things like using water that's way too hot can mess with the internal structure. This creates what scientists call a refractive index mismatch. Basically, the light passing through the material starts to scatter all over the place, which makes it look white to our eyes. It's a really cool optical illusion based in material science, not a chemical reaction. Okay, so we've looked at how the material deals with its environment, but what about how it interacts with us? This is what we'll call the human factor, and it brings up a potential hidden risk that's really important to understand. The key thing we need to talk about here is something called residual monomer, or MMA. Think of it like this. When acrylic is made, tiny little chemical building blocks, the monomers, link up to form these big, long chains called polymers. But sometimes the process isn't 100% perfect. A few of those little building blocks get left behind, unlinked. That leftover stuff, that's the residual monomer. So why do we even care about these little leftovers? Well, for most people, the amount is so tiny, it doesn't cause any problems. But if a denture isn't cured properly and has too much residual monomer, it can slowly leach out and cause some irritation in the mouth. And while a true full-blown allergy is pretty rare, it can happen. This is exactly why controlling the amount of leftover monomer is so critical for patient safety. So, how do we make sure this risk is under control? Well, thankfully, there are really strict international standards that manufacturers have to follow to make sure these materials are safe.
This table shows the official rules from ISO, that's the International Organization for Standardization. You can see it sets limits for things like strength and how much water it can absorb, but the column I really want you to look at is the one called Residual Monomer Maximum. This lays out the absolute legal limit for that leftover chemical we were just talking about.
And you'll see right away that not all materials have the same limit. Most types have to have less than 2.2% residual monomer. But type 2 materials, you'll see, are allowed a higher limit of 4.5%. Now, the standards themselves point out that even these levels could cause issues for some people, which is why manufacturers are pushed to use curing methods that get that level way, way down, ideally below 1%. The takeaway here is that while there's a legal max, the real goal is always to get that number as low as humanly possible.
Phew, okay. We have covered a ton of ground, from physics to chemistry and back again. So, just for fun, let's see what stuck. It's time for a quick pop quiz.
First question. Thinking back to that first comparison we did, which property had the biggest, most dramatic difference between acrylic resin and stainless steel? Was it A, tensile strength, B, modulus of elasticity, C, hardness, or D, color?
If you picked C, hardness, you are absolutely right. With acrylic at 20 VHN and steel at 400, it was by far the biggest gap, making it about 20 times softer. Nice work.
All right, question number 2. What's the real reason behind that mysterious denture whitening we talked about? Is it A, bleaching from your cleansers, B, a structural change inside the resin, C, the growth of little microbes, or D, water getting absorbed? And the correct answer is B. It's that fascinating structural change inside the material that messes with how light travels through it. It has nothing to do with bleaching at all. Fantastic. So there you have it. From its surprising softness to its hidden chemical life, the acrylic resin in dentures is so much more complex than it looks. It's a material that's been perfectly engineered for one of the toughest environments you can imagine, the human mouth. And we've only just scratched the surface today. The remaining sections will be discussed in upcoming parts. The denture. We'll get into the constant search to make them better, stronger, and, believe it or not, safer. So let's just jump right in with that question. I mean, think about it. It's a question that really drives material scientists every single day. We're about to go on a journey into the world of dental polymers, and we'll explore the challenges and some of the brilliant solutions being developed to create the perfect denture. So where do we even begin? Well, we start with the industry standard. Right now, most dentures are made from a type of plastic called acrylic resin. Look, it gets the job done, but as you're about to see, it has some pretty big weaknesses. And here's the core issue. Just think about what a denture goes through. It might get dropped on a tile floor. That's a sudden impact. And it has to withstand the force of chewing, thousands upon thousands of times. Standard acrylic resin? Well, it struggles with both of these things, and that leads to fractures. This really sets the stage for our whole story, the search for something much, much tougher. To solve this problem, scientists have tried all sorts of clever ways to beef up that standard acrylic. It's not always about inventing a totally new material from scratch, but about strategically tweaking the one we already have to make it stronger and more resilient. Now, this is a really crucial point. We need to understand the two key types of strength we're talking about here. First, you've got impact strength. That's for surviving a single hard fall. But then there's fatigue resistance, and that's all about endurance, withstanding millions of little stresses from chewing year after year without cracking. Improving one doesn't mean you've improved the other, and that's a huge challenge. One incredible solution involves adding elastomers, which are basically rubbery materials, into the acrylic. And get this, it can increase the impact strength by almost 10 times. That's a massive improvement. So what's the catch? Well, these high-performance materials are often way more expensive, and that's really limited how much they're used. Another really fascinating idea is to add tiny, super strong fibers into the acrylic. The whole principle here is exactly like putting steel rebar into concrete. Those fibers act like a tiny skeleton inside the denture, stiffening it up
and stopping little cracks from turning into a full-blown fracture. It's a pretty brilliant analogy. Carbon fibers are probably the first thing you'd think of, right? They are fantastically strong, but they come with two huge deal breakers. First, they're black, which, completely ruins the natural look we want. And second, if you can't get that fiber to bond perfectly with the acrylic, it just creates a weak point. And paradoxically, you can end up with a denture that's actually weaker. Okay, so next up, aramid fibers. You probably know them by the brand name Kevlar, the stuff in bulletproof vests. Their performance is just phenomenal. They have incredible strength, and they bond way more easily with the acrylic. The only catch? They're yellow. And while that's better than black, it can still mess with the denture's appearance. Glass fibers seem like a really great option, and they're potentially the easiest to work with. But success here is all in the details. The surface of the glass has to be perfectly prepared to bond with the plastic. And just like with carbon fiber, if that bond isn't good, you end up with a weaker product, not a stronger one. It's a real high-risk, high-reward situation. So, we've talked a lot about strength, but there's another problem with standard acrylic dentures that's actually much more serious. And it has nothing to do with breaking. It's a hidden danger that can pop up during a medical emergency. The answer is probably not what you'd guess. It's not about how it fits or if it fractures. The most dangerous thing about a standard denture is that in certain situations, it can become totally invisible. Take a close look at this chest x-ray. Somewhere in the lower right, there's a piece of a denture. See it? Nope, and neither can a doctor. If a patient, especially someone elderly or in an accident, swallows or inhales a piece of their denture, it's an emergency. But because acrylic is radiolucent, meaning X-rays pass right through it, doctors have no way to locate it. And this right here, this brilliantly shows the solution. Look at the image on the right. That exact same piece of denture is now clear as day. By adding special materials to the acrylic, scientists can make it radio-opaque, which just means it blocks X-rays and shows up on the scan, letting doctors find it and get it out. So how do they do that? Well, this table shows us the scientific trade-offs. To make the plastic show up on an X-ray, you have to add elements with a higher atomic number, things like heavy metals. But, as you can see in the comments, these additives can weaken the material or ruin how it looks. Barium sulfate, for example, it works, but you need a high concentration to see it well, and that weakens the denture. Since modifying acrylic seems to come with so many compromises, some researchers have looked beyond them completely. They've explored totally different types of polymers to see if there's a better starting point out there. For instance, polycarbonates. They have amazing impact strength, but they can warp if you clean them in hot water. Some vinyl polymers are so sensitive to heat, they can get soft at just 60 degrees Celsius. And then you have vulcanite, an older material that actually worked pretty well, but the special equipment you need to make it, well, that's basically a museum piece now. Okay, we've covered a ton of material science. So before we wrap this up, let's do a quick check-in and see what you've learned. All right, first question. Think back to that table of additives. Which one of these makes a denture show up on an X-ray, but can also weaken it if you use too much? And the answer is B, barium sulfate. If you got that, you're absolutely right. Remember, we saw that you need about 20% of it to get good visibility, but that has a deleterious effect on its strength. Nicely done. Okay, one more for you. This one is about those reinforcements we discussed. Which of these high-tech fibers is famous for being in things like bulletproof vests and has that distinct yellow color?
That's right, it's D, aramid fiber. That's the generic name for materials like Kevlar, which we talked about having incredible strength but that problematic yellow color for dental work. Great job. So I think the key takeaway from all of this is that building a better denture is just a delicate balancing act. Every single potential improvement, whether you're talking about strength or looks or safety, it all comes with a scientific trade-off. There isn't one magic bullet, just this constant, careful process of innovation.
So, what's next on the horizon? Well, the future probably isn't about finding one single perfect material, but about smartly combining all these technologies. Imagine a denture with a radio-opaque core that doctors can see, reinforced with clear glass fibers, all made from a new copolymer with amazing impact strength.